Hey, today we're talking about limits, more with limits, the squeeze theorem, specifically so that we can do some special trig limits. So the squeeze theorem, you don't have to memorize it, just be aware of it and why we used it. This theorem concerns the limit of a function that's squeezed between two other functions. Each of those functions has a limit that we know, and it will be the same limit at that given x value. So you see we have this function g, and that's the limit we could find analytically, and then function h, for example, could be a limit we could find analytically. Since they both have a limit as x approaches c of that, whatever that value is there, we know that any function that's squeezed between them will have the same limit at that point. So the squeeze theorem, also called the sandwich theorem or the pinching theorem, here's the exact theorem. If some function h, and in this example h is the red line here, is less than or equal to a different function f of x, and that's the goal, is trying to find that limit of f of x. In this case, f of x is the blue line. And it's less than or equal to a function g of x, and that's this black line, for all the x's in an interval containing c. So some group of x values around a particular one we're looking at. In this case, we're looking at x equals 0 here. So whatever happens over here, we don't care, but as long as around c, that value, the f of x, the function we're trying to find the limit of, is squeezed between. So those y values are between those two. And if limit of h of x is that bottom function, as x approaches c, equals some value, which is the same value that the limit of g of x, that top function, is as x approaches c. So both the top and the bottom function not only have to be above each other, but they have to equal the same limit. Then the big conclusion is that the limit of that middle function is going to be that exact same value. Hopefully that's pretty obvious, and you don't have to memorize that theorem, just using it to explain this particular function. We need to know what the limit of sine x over x is. That's a key trig function that we need to know the limit of as x approaches 0. Since we know cosine of 0, if we use direct substitution there for 0, we know cosine of 0 equals 1. And the limit of anything, any constant, will be that constant, so the limit of g of x will be 1, and you can see that that y value, both the left and the right of the black function and both left and right of the red function, approach 1 as x approaches 0 on the left and the right. So we can say that the limit of sine x over x equals 1 by the squeeze theorem. So the thing you have to know is that the limit of sine x over x as x approaches 0 equals 1. There's a similar proof for the limit of 1 minus cosine x over x as x approaches 0, and that equals 0. You don't have to know those proofs, you just have to memorize those trig limits. And we will use them as building blocks for any other trig functions that have sine or cosine in them. So here's an example. If we're trying to find the limit as x approaches 0 of tan x over x, remember the first step is always use direct substitution. So if we put a 0 in there, tangent of 0 is 0. And if we put a 0 in there, we'll have 0 in the denominator. So that would give us 0 over 0, which is indeterminate, which means sometimes it equals some answer, sometimes it equals a different answer. So that means we need to do more work. One thing we would try to do is maybe cancel, but you can't cancel x's. This x is inside of tangent, so we can't cancel, but we can rewrite tangent as sine x over cosine x. So tangent x is rewritten as sine x over cosine x. That's a trig identity you need to know, divided by x. So instead of writing dividing by x, we can simplify that complex fraction by rewriting it times 1 over x, because dividing by x is the same as multiplying by the reciprocal of x, and the reciprocal of x is 1 over x. So that's rewritten as sine x over cosine x and then times x. But multiplication can be done in any order, so I'm going to be a little sneaky here and put the x first and then the cosine x second, because I can break up this fraction. Multiplication's cool with fractions because you can break them up again, just like you can put them together. So here's how we had two fractions, we put them together using multiplication. We can break them up, sine x over the x times, and then we keep that cosine in the bottom. So the denominator, sorry about that, the denominator is still cosine x times x. That's cosine x times x. The denominator is still x times cosine x, but to keep that cosine x in the denominator, I put a 1 on top, and now I have two fractions. If you multiply them back together, you get back to this. But the goal here, notice we got sine x over x separate from the 1 times 1 over cosine x. We know the limit of this. The limit of that function as x approaches 0, which is what we're trying to find, is 1. That was our theorem on the previous page. So this answer here will be 1. And then we just need the limit of 1 over cosine x as x approaches 0. If you use direct substitution here, cosine of 0, if you think about your unit circle, is 1. So we have 1 times 1 over 1. So our final answer here is going to be 1. So the limit as x approaches 0 of tan x over x, using our special trig limit here, is 1. If you also look at the graph, you can see that the limit as x approaches 0 from the right and the left is going to be 1. That's the usefulness of those two special trig limits, is to be able to analytically find the limit of things with trig functions in them. Another example we would use it for is trying to find the limit as x approaches 0 of sine 4x over x. Now we're going to use an extension of the sine x over x identity. Sine of anything over that same anything as x approaches 0, the limit as x approaches 0, is still going to be 1. So if we had 4x here, as long as this is also a 4x, that will still equal 1. So this doesn't just have to be x and x. As long as these two match, the argument of sine and the denominator are the same, then we will have this, we will be able to use that same trig limit theorem. So we'd like this to be a 4 down here, but it's not. So in order to force there to be a 4 down there, I'd like to multiply that denominator by 4. But to keep it an equivalent fraction, I have to multiply by 4 on the top also, because now I'm multiplying by a clever form of 1, and anything times 1 is still itself. But it's going to be disguised. So this 4 cannot be multiplied times this 4x here. This 4x is inside of sine. It's like inside of a square root or inside of parentheses. It is not to be touched. But this 4 could be written out in front. So 4 times sine of 4x. We don't write the parentheses, but they really are there. And then this down here, I'm going to write 4x. So now you notice this part is our special trig identity or limit, not identity. So the limit of this as x approaches 0 is 1. So we have 4 times 1. So the answer for this whole thing is 4. So use this trig limit and the sine x over x to simplify problems that you can't do analytically without that. Another topic that we use a lot in calculus is velocity. The velocity of a free-falling object whose position is given by s of t equals negative 4.9 t squared plus 199.6. Now this negative 4.9 is constant. It will be the same anytime you're using meters because the pull of gravity is negative 9.8 meters per second. And the formula for position always is the pull of gravity divided by 2. So negative 4.9 will always be there. This number changes based on the initial height. This is the initial height of the function, of the object, initial height or initial position of the object that we are throwing or dropping. S of t is what our calculus book uses for position or height. I believe in physics you use a of t, maybe. But S of t is what we'll use for position in calculus. So we're trying to find the velocity of a free-falling object. They've given us a velocity equation. Sine of a, this a here is going to be a constant. They will give us a value for that. So a is going to be a constant, and this a is going to be a constant. That's going to be this here. I know it says t equals 2, and don't put 2 in for t. This means the original function without any numbers, any new numbers in it, just the original function here. This thing right here is going to go here for s of t. S of a is where you put the 2 into the original function and get that answer. So whatever they give you in your homework for a, that'll be this. Make sure you put that number in. This is an example from your homework. That is a common area that students get stuck on, so I'm telling you about it right now. This is going to be the 2 also. So in this problem, because t equals 2, we really are looking at this. T approaches 2, and then s of 2 minus s of t, the original function, all over 2 minus t. So that's what it's going to look like. So this thing will be in the directions of your homework, and they'll give you this in the problem. So first we need to find s of 2, which means we're going to plug 2 into the function, negative 4.9 times 2 squared plus 199.6. which is 180. So we have the limit of 180 minus the original function, so minus negative 4.9 t squared plus 199.6 all over 2 minus t. And notice I'm not using equal signs, so I'm going to just drop that word limit and just work on simplifying. So I have 180 minus that whole quantity, which means I'm going to do 180 minus each thing. So 180 minus 199.6 is negative 19.6. And then minus the negative 4.9 is plus 4.9 t squared. And that's all over 2 minus t. If I do direct substitution right now with that 2, I still have a 0 in the denominator. So that leads me to believe I should do something more with the numerator. Probably factor, so I can cancel out that denominator. So factoring it as is kind of tricky. I'm going to factor out a negative 4.9. That negative 4.9 I'm getting from here. That's where I think that's what I think will work. So 19.6 divided by 4.9 give me the 4. So a negative 4.9 times 4 is negative 19.6. And then I take a negative 4.9 out of the 4.9 t squared, so I have a minus t squared. Now 4 minus t squared is the difference of squares, so I can factor that. First times first would be 2 times 2, that gives me the 4. And last times last is a positive t times a negative t. And then that's going to cancel with the 2 minus t. Now that's what I wanted to happen because I don't have a denominator anymore. So I can do direct substitution now. So no equal signs means I didn't have to keep writing limit, but now I'm actually going to write the limit because I am going to do the direct substitution. So I have negative 4.9, 2 plus t equals. So plug that 2 in there. I'll have 2 plus 2, which is 4. Negative 4.9 times 4 is my negative 19.6. That's meters per second. That's the velocity of the object at time t equals 2 if it started at a height of 199.6 and there was no initial velocity on it, just the pull of gravity. When you get used to working with position functions, velocity and acceleration, you notice that position functions will have a higher power than the velocity function. Where's my velocity function? Here. So whatever power this is, it's usually going to be a power of 2. This degree will be 1, and then acceleration will be 0 for the exponent. Here's that f of x plus something composition function. I'll just do an example like this because it's on your homework. F of x plus delta x minus f of x. Delta x itself is one function. So we're going to replace that x plus delta x in here. So we'll have x plus delta x squared minus 4x plus delta x minus the original function, distribute that negative through there, all over delta x. Foil this out. Do not just put the power of 2 on there, but foil it. So x squared plus 2x delta x plus delta x, that quantity squared. Distribute that 4 in there, minus 4x minus 4 delta x. Distribute that negative, minus x squared plus 4x, all over delta x. Combine like terms, the x squareds cancel, the 4x cancels, and I have 2x delta x plus delta x squared minus 4 delta x, and that should be it, all over delta x. So right now if I try direct substitution, it still doesn't work out, so I'm going to factor out the delta x. I'm running out of time. Let's see if I can make it. Now the delta x will cancel. You can do direct substitution, put 0 in for the delta x, so you get 2x minus 4. Did it. Here's your homework. Have a great night.